Okay. Hello, everyone. So this week we have covered in face-to-face lectures, covered the conjugacy relationship in groups. And then I have talked about the permutation groups and permutations in general, right? Next week, I'm going to talk about the rotations, and then, well, basically in the next week, I'll be talking about the symmetry, especially I'll talk about the electromagnetism and the weak interactions and things like that, all right? So I'm going to basically, I would like to basically enter into the physical discussion side. So unfortunately, this week too was actually completely mathematical, right? Just keep this in mind. So in here, in this R, I'm just going to summarize what that thing is, conjugacy relationship is, and then also I'll summarize what the topic about the permutations. Okay. So in any case, so the conjugacy relationship is something like this. It's kind of a complicated relationship. So it's like the similarity transformation for matrices, that we define it for an abstract group, actually. So it turns out that this relationship is important for some group representation theory, but we are going to see why they are useful much later, right? Like towards the end of the semester, we are going to see why that's relevant for us. So for us, it's going to just, it looks like complicated, some abstract discussion actually. But let me first give you the definition. So we have a group, G is a group. It doesn't matter what kind of a group it is. I can also define it for infinite groups as well. It doesn't matter. There are two elements, G and I don't know, H within this group, right? We say G is conjugate to H, right? And I'm going to show it by this symbol, G is conjugate to H, if there is an element, a third element in the group such that, right, basically a similarity transformation, applied on H gives us the this element G. So in a way, this is some kind of a transformation between elements of the group. So you just transform this element H into that one by using this kind of a transformation. And if that's the case, then we say that these two elements are conjugate to each other. So for the case of matrices, we would say that G is similar to the matrix H, right? So that's essentially a similarity transformation. If I can convert a matrix through a similarity transformation to another matrix, you will say that these are similar matrices. So the conjugacy is actually an extension of this idea to an abstract group, actually. You can think of it like that. Okay. In any case, it appears that conjugacy is a similarity transformation. Conjugacy is an equivalence relationship. Equivalence relation. So in mathematics, this actually means three properties. I mean, for a relationship being an equivalence relationship, you need three properties: that every element is equivalent to itself. There's the symmetry thing. If an element is equivalent to H, then H is also equivalent to G, right? So as a result, it doesn't matter which one is equivalent to which, they are equivalent to each other, actually. But that captures the idea. And then there's this transitive property. So if G is equivalent to H and H is equivalent to K, then this implies that G is equivalent to K, right? So elements which are equivalent to the same element are equivalent to each other. Friend of my friend is a friend of mine, right? Or something like that, okay? So as a result, in any case, these are very simple proofs actually. So I can prove this by just noticing that G can be written as identity times G times identity inverse. Here we have this, like if G is equal to F H F inverse, then I can write H as like F inverse G F, but F can be written as actually the inverse of the F inverse. As a result, it has the same form. And whatever, I mean, let me not do this. Right? This is a very simple proof, actually. Okay. In any case, so with conjugacy comes, there's this concept of conjugacy classes. These are actually the equivalence classes. If you know this equivalence relationship in some mathematical set theory courses, if you have taken any, I mean, if you are familiar with this equivalence idea, then probably you know what this means. So conjugacy classes. Basically, we are going to use this notation. So this is basically the set of elements conjugate to G. Okay, conjugate to G. So as a result, this is the set of elements H, where H is conjugate to G. Right? So of course the group is important in here. So I have to do this within a group. So somehow the group has to be specified. So a conjugacy relationship in a group might be different than a conjugacy relationship in a subgroup. So two elements might be conjugate if they are considered elements as of the full group, but they may not be conjugate if they are considered as elements of a subgroup, for example. So the group is important, but I mean, I'm just writing this thing down for simplicity, basically, right? So in any case, so basically H is an element of G if and only if H is conjugate to G. Okay? This then tells you that, all right, so if H and H prime is in G, then this implies that H and H prime are conjugate to each other. This class contains G itself and things like that, right? I don't know, there are. So the properties of the conjugacy relationship, equivalence property, can be used to state these. Basic idea is this. Let's see. If G is equivalent to H, then the conjugacy class that they both generate are the same, right? Right? Two elements are conjugate if and only if their conjugacy classes are the same. Whatever. If they are conjugate, then they generate the same conjugacy class. Okay. Yeah, whatever. I don't want to write this thing down in words, but that's essentially the idea in here. So the main theorem from set theory is that it says that the two conjugacy classes are either the same, are either equal, or they are disjoint. Okay. So basically this says that if I have like, if G and G prime are elements within the group, then we either have the conjugacy class that G belongs to is the same thing as the conjugacy class that G prime belongs to, or, so that's the first situation, that's the second situation, or these two conjugacy classes do not have any intersection, right? Their intersection is an empty set. Okay, So why? Well, I mean, the first one corresponds to the situation where the G and G prime are conjugate to each other. The second one corresponds to the case where the G and G prime are not conjugate to each other. So if they are not conjugate, then the corresponding conjugacy classes cannot have an intersection, because in that case, they would be conjugate to the elements in the intersection or something like that. Okay? As a result, you have these two situations. So this then tells you that the conjugacy class is some kind of a partition of the group into these smaller sets, right? Something like that, right? So these are basically conjugacy classes. Different conjugacy classes, they don't intersect. And you can think of the group as the union of these conjugacy classes. So there are a few things like identity. E is conjugate only to itself. Basically, this is true for every element. This implies that the conjugacy class has only one element. So therefore, let's see it like this. Conjugacy class has only one element. Okay. There are situations, there's also one special case. Again, I'm going to talk about this later. So if G is a abelian group, implies that, so in this case, for example, if you just look at this conjugacy relationship, for example, since this is an abelian group, the elements can change, do commute. In that case, the conjugacy basically is not going to, I mean, if you do a similarity transformation in here, you're not going to get any new element, right? So this then tells you that the G is conjugate to H if and only if G is equal to H, right? So conjugacy relationship is the same thing as the equality relationship. So that means every element is conjugate only to themselves, which therefore implies that the conjugacy class in that case is that single element in here, right? I mean, the case for identity is going to be, for an arbitrary group, is going to be valid for an abelian group for every element, right? So essentially, any element of a group that commutes with everything forms its own conjugacy class. So it's only conjugate to itself. And so therefore its conjugacy class contains a single element. All right, that's it. I mean, that's it for conjugacy. But since this is going to be an important relationship, so in every group that we need to actually establish that conjugacy relationship. So in the permutation group, for example, we are going to find the condition for two permutations being conjugate to each other, and for the rotation group as well, right? So just keep this in mind. So for rotation groups too, we have some certain ways of doing this. So again, I mean, this is something that I'm going to come back later, but at this point, let's just define it like that, and that's basically it. So in any case, next we talk about the permutations. So let me write permutations in here. So you might have X as set of n objects. Okay. Usually, we just take these objects as numbers from 1 to n, because this is a nice notation, right? Let's say this is for example, but I'm going to use this example in here, the permutation. Right? A permutation f on x is a function that maps elements of x into elements of x such that F is 1-to-1. But 1-to-1 implies that it also is onto, and so therefore it's the same thing as well, being invertible, right? I don't know. I mean, let's just talk about the set of 3 elements. 1, 2, 3. Sorry, I'm going to do it like that, right? So 1, 2, 3, for example. F can be a function that maps 1 into 2, and 2 into 3, and 3 into 1, for example, right? F is a map like this. So whatever, I mean, we just consider this as some kind of a function, right? So in any case, if F is 1-to-1, in that case, it is necessarily onto because this is a finite set. So therefore, inverse exists. Okay. So this then tells you that, I mean, we also can see that the composition of these permutations is a permutation. So therefore, the group Sn, so this basically the set of all permutations of n objects, right? So Sn together with the composition, composition is a group. So Sn is called the symmetric group. I mean, that's the name given. Why that name is given, I don't know. I mean, I don't have. I mean, there's some kind of historical reason for that, but I don't know what. So the number of elements or the order of the symmetric group in here, order of Sn, is n factorial. There are n factorial such permutations. So let's say it like this: identity permutation. Permutation. It's basically a permutation where every element x is mapped into x, right? For every for all x in x. Obviously, I mean, this is defined like that, and I'm going to use the E symbol again for expressing the identity permutation. So in any case, if I have like 2 permutations f and g in Sn, I'm going to use fg to express f of g. Okay, I mean, basically the multiplication operation in that group is the composition of functions. So this is the calculus notation for the composition of functions. That essentially means that the value of fg at x, I mean, fg is a function, so that's f of g. Its value at x is equal to the value of f at g of x, right? If you remember, that's the notation in here. So therefore, in here, the second one in here, right? The second symbol in here. So the permutation, the rightmost permutation is applied. The rightmost permutation is applied first, right? Just keep this in mind. This is the rule. If I have the composition of 2 permutations, it's the rightmost one that I'm applying. So that's also consistent with the calculus rule, right? Just keep this in mind. There are actually various notations for permutations. So let me remember this one. So one is called the tabular notation. Now let me first copy this. Sorry about that. I think I'm going to use some electronic magic in here to copy this in here, right? Sorry about that. Okay. So let's just consider this permutation in here. So we usually write this permutation as it's just a horizontal list of numbers, for example, and 2 rows basically, And then in the row below, we just write down the elements where each of these elements are mapped into. So in that case, for example, this permutation is the permutation where 1 is mapped into 2, 2 is mapped into 3, and 3 is mapped into 1. It's basically shown by that notation. Okay. So the identity permutation, for example, would be written as like 1, 2, 3, 1, 2, 3, for example. So that's the one notation. Okay. So I'm still talking about this the same f in here. So let me introduce one more thing. Okay. So let me make this minimized. So instead of using this kind of a notation, pictorial notation, we usually write these objects only once, 1, 2, 3, for example, and then they draw the arrows between these elements. So instead of writing 1, 2, 3 twice in here, I just write them once only, right? So in that case, 1 is mapped into 2, 2 is mapped into 3, and 3 is mapped into 1. Okay. So you can draw pictures like that. These are usually called cycles. All right. And this is going to be the basis of what we call as the cycle notation of permutations. As a result, I'm just going to formally define it like this. So I'm just going to say that. So x1, x2, xr is called an R cycle of permutation G. It's called an R cycle of a permutation G if basically G maps x1 into x2, G maps x2 into x3, and so on. Let me be completing here. XR minus 1 into XR, and then XR into X1. Okay. So I have like this list X1, sorry. I'm going to do it like that, right? So I don't know how many R's in there, but let's say that there are 6 R's in here. So X2 is mapped into X3 and so on. And then we have XR minus 1 in here and XR in here. So in this thing, basically every element is, every object, sorry, that's an object of the set X basically. This is mapped into the next element. So we just show the cycle by that notation. Okay. So in any case, so since these actually form a cycle actually, there is no starting point and an ending point because somehow the permutation is onto every element is also mapped by something. So we should have some kind of a cycle like that, a complete cycle. In that case, the starting point is not important. So as a result, I can start this cycle from, for example, X2 and X1 like that, right? So X2 might be the starting point and X1 might be the last point or whatever. So as a result, I can start it anywhere I want, right, in this notation. So the cycle notation is this cycle notation for a permutation. Well, it's basically the list of cycles. So as a result, this cycle permutation, so in this cycle picture, sorry about that. If F is a mapping like that, F maps 1 into 2 and 2 into 3 and so on. In that case, I'm going to write F as this cycle in here. Right, so in that case, this is a permutation called 1, 2, 3. As I said earlier, I can write this thing down as 2, 3, 1 or 3, 1, 2. It's basically the same cycle. I can express the same cycle in different ways, right? There are some certain things in here. So for example, this cycle in here. So let me call this like, I don't know, let's say G is that cycle where it's basically the same triangle, but the order is the opposite, right? In that case, G is equal to 1, 3, 2. I can express it as 3, 2, 1 or 2, 1, 3, whatever. But you can notice that it's basically the same triangle, but the order is reversed. So in that case, it's kind of easy to see that G is basically the inverse of F. Right? I mean, these two are basically inverses of each other. So, okay. So, yeah, whatever. I mean, so you get the same cycle. So let's say it like this: 1, 2, 3. The inverse of 1, 2, 3 can be obtained by just writing this list in the opposite order. Okay. So that's the first thing. Let's say it like this. I don't know. I mean, there might be more complicated cycles, like, I don't know, let's say it maps 1 into itself and 2 into 3. And I don't know, 4, 6, 7, 5, for example. Sorry, I think I don't want to make a mistake in here, so therefore that's why I'm careful. So let's say that F is this permutation. So F is an element of a permutation S7, let's say. So F is a permutation of 7 objects. In that case, I'm going to write this permutation as 1, 2, 3, and 4, 5, 7, 6. It doesn't matter in which way I write them down, so I can write this down as like 3, 2, and then 5, 7, 6, 4, 1. That's a possibility. Okay. So the convention usually is that if you have a 1 cycle, I mean, if you also have some well-known objects, and if you have a 1 cycle, people usually do not show 1 cycle, right? So that's convention. Do not show 1 cycles. Okay. If identity, for example, is considered as an element of the S7, then in that case, identity is basically is a permutation which sends every element to itself. So as a result, the identity has 1 cycles only, right? So every element is mapped into itself. In that case, if I actually use this convention of not showing the 1 cycles, in that case, I would get an empty list in here. So people usually do is like they actually show this by the letter E, right? So that's the another convention too. So that's the convention. So we are going to use the letter E for expressing the identity cycle. Identity permutation. Okay, there are a few things in here. Okay. So F is equal, let's say, I don't know, F is an if F is an N cycle. All right, let's say it like this. All right, it's a permutation that contains this N cycle, for example. It might also contain some other 1 cycles as well. I don't know. I mean, I have just written this thing down. Right? Then the nth power of F is equal to identity. Okay, so if you have an N cycle, I don't know, let's just say it like that. So the nth element is actually converted into 1. Yeah, whatever. So, I mean, it's quite easy to see what happens in here. So F squared would be a permutation where 1 is converted into 3 and 3 is converted into 5 and so on. I don't know, there might be 1 or 2 cycles in here depending on whether n is even or odd. If it's odd, then it's also an n cycle. But if n is even, then there are like 2 cycles in here or whatever. I mean, there are some certain things like that, but you can kind of see that f to the power n, when you apply it to identity, to the first object, you get the first object. When you apply it to the second object, you get the second object, and so on. This basically tells you that the nth power of an n cycle is equal to identity. So therefore, an n cycle has order n, right? An n cycle has order n. All right. Yeah, there are lots of things that I need to talk about. So there's something called a signature, or sorry about that. Let me just do this step by step. A transposition is a permutation, let's say, that has a single true cycle. And the rest is one cycles, right? And the rest is one cycles, right? So I don't know, for example, in S4, for example, so 1, 2 is a transposition. Okay, and similarly, 2, 3 is also a transposition, right? It's just a permutation of 2 elements. Okay, so I don't know how many transpositions are there. I think there are 6 transpositions or something like that. But 1, 2, 3, 4, for example, is a product of 2 transpositions. Okay. In a way, a transposition is the atom of permutations, actually. It's the simplest possible permutations, just the exchange of 2 elements, right? Exchange of 2 objects. The idea in here is that I can express any permutation as a successive application of transpositions. So this is actually something quite simple to prove. So any permutation can be written as a product of transpositions. Okay, I think I'm going to give this example. So 1, 2, 3, ... n. So I can write this thing down as the product of 1, 2 with 1, 3 with 1, 4 with ... 1 n. Okay, this is one example, for example. Here, just keep in mind that all of these are permutations where this one is applied first. So this is not a cycle notation of a permutation. Basically, the permutation has this cycle notation. So these are like 2, I don't know, many transpositions multiplied together. So they don't actually commute with each other. So that's one of the important things, perhaps. They don't commute with each other. So let's just keep this in mind. So here, for example, if you just consider what happens to these individual elements, you can kind of see what's happening here. So, for example, this one, if I evaluate the value of how to which object this one is going to be sent by the first permutation, you can see that it's first sent into 2. And then this doesn't change, this doesn't touch 2, it just leaves at its place. This doesn't touch 2, and so on, right? So as a result, sorry about that. only the first permutation changes 1 into 2, all the other permutations keep 2 at the same place. Now, what happens if I apply this set of permutations to 2? So you can see that 2 is first converted into 1 by the first permutation, and the second permutation changes 1 into 3, right? So as a result, this 2 will be converted into a 3. And so on, right? You can just check that. Or, for example, n will be converted into 1. So therefore, that product actually gives you that permutation whose cycle notation is this one. Okay, I mean, just check yourself, right? I don't want to go into some detailing here. Okay, so there are in here, for example, n-1 transpositions. So I can express an n cycle as a product of n-1 transpositions, for example. Okay? So the result, just write any permutation in terms of the cycle notation, and then, well, you can see that it's basically can be written as a product of transpositions. Okay, so that's the first thing. Second thing is that any permutation can be written as a product of transpositions, but it can be written in many different ways. So let's say it like this: if f is a permutation with alternative expressions as a product of transpositions. So I'm going to do it like that. So let's say that f can be written as a product of transpositions like that. And they don't have to commute with each other. So I don't know. Let's call this like tk, or I can write f as like t prime 1 product with t prime 2, and so on, t prime l. So l might be bigger than k, for example. So the claim is that k and l have same parity, meaning that k is even if and only if l is even, and k is odd if and only if l is odd. Okay. So this is some kind of a theorem, actually. So let me write theorem here, but it is quite hard for me to prove in a mathematically complete way. So as a result, we are just going to accept this. Okay. But this is the basis for our definition of signature. So in the first case, for example, when this k number, this integer is even, we are going to define that, say that the f is an even permutation. And if k is odd, then I'm going to express it like f is an odd permutation. Okay. In any case, signature is signature of f. So I'm going to use epsilon f notation for that. And some people actually use -1 to the power f. That's basically -1 to the power that number k, which is the same thing as, sorry about that, I need to make this smaller, which is the same thing as -1 to the power l, right? There's a -1 in here, right? Okay, so as a result, this is a number which is plus or minus. So basically, we say that f is even. That's the same thing as epsilon f being positive +1. That's the same thing as, right? F can be written as a product of an even number of transpositions. Okay, And similarly, so I'm going to write dot dot in here. Similarly for odd, right? In that case, the signature is equal to -1, and that basically means that it can be written as a product of an odd number of transpositions. Okay, so there are these examples in here. Every transposition is odd. Is odd, right? So 1, 2 is an odd permutation. It implies that the signature is equal to -1, right? Because every transposition is equal to itself. So as a result, you can express it as a single transposition. Identity is even. Why? Because identity can be written as this transposition multiplied with itself, right? Every transposition is equal to its inverse, so therefore the product of the same transposition twice gives us the identity, for example. So yeah, whatever. So this then tells you that the identity is an even permutation. Okay. So there's this theorem in here that says that the epsilon in here, the signature, let me write the signature epsilon satisfies this rule. So if you have like two permutations, the signature of the product of two permutations is equal to the products of the signatures. So this tells you that, for example, product of two odd permutations is an even permutation. This is quite easy to prove. There is no difficulty in here. Once you accept the basic fact, this is quite easy to prove. This basically says that the epsilon, which basically associates every permutation with a number from the set +1 and -1. Okay, I can think of this as the group C2, cyclic group C2. So this is a group homomorphism. Okay. So signature is actually a very nice thing. It's basically the Levi-Civita tensor. So for example, I don't know, Levi-Civita tensor. I don't want to describe it in here because it has nothing to do with this course. But you remember the Levi-Civita tensor, for example, I don't know, 1, 3, 2, for example, right? That's basically signature of the permutation that changes. I'm going to give this in tabular notation. For the permutation that changes 1 into 1 and 2 into 3 and 3 into 2, right? So basically think of these subscripts as a permutation of 1, 2, 3 into a new order, right? So the signature of that permutation is our Levi-Civita tensor. But the Levi-Civita tensor has this additional property that, I mean, if there's a repeated index, that's equal to 0, actually. So in that case, we don't have any permutation here. Whatever, I mean, so if there's a repeated index, the Levi-Civita tensor is 0, but if there's no repeated index, then I can think of this as a permutation of labels from 1 to the dimension of the space. Here we're talking about 3-dimensional space. And so as a result, I can therefore give a clear meaning in terms of the signature of the permutation. Okay, so just keep this in mind. Sometimes this kind of thinking is useful. I basically explain this as some kind of a bonus. All right. There are two things in here. All right. Many things, sorry. First of all, the conjugacy in here. In Sn. So let's say G and H in Sn. The idea in here is that the G and H are conjugate if and only if G and H have the same cycle structure. So basically, the cycle notation becomes important for because of that reason. So suppose that G is the permutation, like I don't know, 1, 5, 7, let's say 2, 3, 4, 6, for example, and let's say that H is a permutation. Let's say 5, 2, 3, 1, 4, 7, 6, for example, right? 1, 2, 3, 4, 5, 6. So both of them are basically elements in S7. So the claim is that since they have like the same number of 1 cycles, same number of 2 cycles, same number of 3 cycles, which is 0, and same number of 4 cycles, they have the same cycle structure, right? The only difference between them is that the elements of these cycles, the objects that takes place in these cycles, they are different. So in any case, because of that reason, G is conjugate to H. Okay? And we have the opposite as well. If they are conjugate, then you can show that they have the same cycle structure. Sorry, there's some kind of a connection that you can actually kind of establish. So let's say it like this. So if G is equal to FH inverse, in that case, you can show that GF is equal to FH. So that means G of F of X is equal to F of H of X or something like that. So in any case, if H, sorry, I have a problem here. All right. I mean, if H has this cycle structure, for example, yeah, just forget about this because I cannot, I mean, in the notes, this is the reasoning in here is explained as a result. Let me not do it. Okay, so you can actually find by just looking at these cycles and the objects contained in these cycles, you can find the map that does the similarity transformation. All right. There is one other thing. It's the concept of a permutation matrix. Right? P, right? A matrix is there called a permutation matrix is that, right? Sorry. A permutation matrix P. It basically satisfies this property. So first of all, P is a square matrix with elements. I mean, the matrix entries are 0 or 1. Okay. And the second thing is that every row of P contains only one entry equal to 1. And number 3 is the same thing for every column. Right, the rest is the same. So if these conditions are satisfied, then P is called a permutation matrix. So one example is this, right? So in any case, so that's a permutation matrix, for example. Why do we call them as permutation matrices? So let me just explain this, and that will be the end. So we just define the standard basis vectors for column vectors, right? So these column vectors are standard basis vectors. Standard basis vectors. I can think of every square matrix as a transformation of these column vectors, basically. But the idea in here is that the P applied on the standard basis vectors gives us one of the other standard basis vectors. So P applied on E1 gives us E2, P applied on E2 gives us E1, and P applied on E3 gives us E3, for example. So as a result, because of that, P can be considered as a permutation of the standard basis vectors. P is a permutation of standard basis vectors. Right? From that point of view, that P, for example, is equivalent to a permutation where E1 and E2 is just exchanged and E3 is left fixed. Okay, so therefore this is like equivalent to the permutation 1, 2, for example, right? So in any case, you can actually think of them as like matrix representations of permutations too. At some point we are going to need these kind of examples. So as a result, this is going to be a very nice example of some particular matrix representations of groups. Okay, let me stop here.